Okay, hi folks, welcome back to part 2 of this, lecture 5 of the experimental design and analysis series in Core Skills. The job for the next part of the lecture is to think about the fact that significance, statistical significance, is not the same as effect size, and that means that just because a test turns out to be significant doesn't mean that you've uncovered a biologically interesting effect. So let's have a look. Oh, before we go on with that issue, I just want to finish something I was saying before the break about different types of error. So I introduced the idea that we might have found a statistically significant difference between our two groups of bed bugs, for example, and yet the difference might not have been real, in the sense that whatever the p-value, there is going to be some probability that what you've observed is a rare chance event. Even if there's a big difference between the two means, that is possible under the null hypothesis, even if it's rather unlikely. So if you reject the null hypothesis by mistake, then what you've done is you've committed what we call a type 1 error. So type 1 errors are rejecting the null hypothesis when in fact the null hypothesis is really true. And the nice thing about type 1 errors is, I mean, they're not great, we don't want to make them, but at least we know exactly what the probability of making a type 1 error is. The probability of making a type 1 error is alpha, that is the threshold below which we consider a p-value to be significant. So if we start a study and we decide that alpha is going to be 0.05, which is most commonly the case, then what we're saying is we know that 5% of the time, if the null hypothesis is true, we're going to make a type 1 error. We're going to accidentally reject the null hypothesis, because that's what the p-value means. The p-value tells you how likely the data are to crop up under the null hypothesis. If the answer to that question is 4% of the time, then if the null hypothesis is really true, 4% of the time you run the test, you're going to get a false significant result. So as long as we know what that means, we know what alpha means, we know what type 1 errors are, then at least we're kind of in control of the situation. And we can reduce the probability of making a type 1 error by lowering the threshold. And that's actually quite common. It's something we might do in a study where we really care about making a type 1 error. So for example, if you're trying to introduce a new drug to which perhaps might improve outcomes from COVID, but has some unpleasant side effects, you're only going to want to introduce that drug if you're absolutely convinced that the positive effect that you seem to have had on COVID outcomes is not just a type 1 error. So we want to increase our confidence in the results, so we decrease alpha, would be the general philosophy. The problem with that is that if you really clamp down on type 1 errors, you risk making the opposite kind of mistake. So a type 2 error is the opposite kind of mistake, where you do not reject the null hypothesis even though it's actually not true. So the probability of making a type 2 error is conveniently called beta, as opposed to alpha, the type 1 error rate. And essentially beta depends on the statistical power of the test that you've got. So if you've got a really big sample size, a really powerful statistical test, then the chances of you failing to reject the null hypothesis when you really should have done are going to be very small. So in that sense, as an experimenter, we have some control over beta. If we design a really powerful test, beta is going to be small regardless of what alpha is. So in going back to our sort of medical example of like we're doing some critical medical trial where we want to be absolutely certain that our COVID vaccine works, then what we're probably going to do is design a massively powerful test, and that's exactly what they're doing with COVID vaccines. They're trying to test thousands and thousands of people so that your beta, your type 2 error rate is low, even if your alpha is also quite low. So that way you can guard against failing to spot that your vaccine is good, but also you can guard against using the vaccine when in fact it doesn't work. Okay, So all of this is going to turn out to be relevant to this concept of significance and effect size that I was talking about, in some senses anyway. So let's go back to the example where we first learnt about doing stats tests and generating p-values, and it was this example with the mice that we're treating with calcineurin inhibitors, and we're looking at the swimming speed of their sperm. And if you remember, on day 1 we found quite a clear, strong effect, a significant effect of the drug on the swimming speed of the sperm, with the treated mice in the black bar here having lower sperm swimming speed than the control mice. But by the time we got to day 5, that effect appeared to have disappeared, at least although there was a small difference on the graph, a small difference between the means. Our test showed that that kind of difference was quite likely to arise by chance under the null hypothesis, so we weren't able to reject the null hypothesis. But looking at that, you might think, well, maybe that's an error. Maybe we should have rejected the null hypothesis. Maybe there is really still a small residual effect of the calcineurin inhibitor, but we failed to do that because essentially we didn't have a powerful enough test. In other words, maybe we've committed a type 2 error here. How do we know? Well, one way of knowing is to go back and study it in more detail, and crucially to produce a more powerful test where the probability of making a type 2 error is lower. So let's imagine we go back to the mice and we sample many, many more mice in the control and treated groups 5 days after the treatment is finished. So we have a much more powerful study. Do we find a significant effect? So here are some data where we've gone from a sample size of 6, as was the case in the original study, which gave us a non-significant difference between the 2 treatment groups, even though there was a small difference between the means. Here's what happens when we ramp up the sample size. Ramping up the sample size, the means have actually stayed fairly similar. The difference between the means is still about the same. It's small, but now it's actually judged to be significant by the t-test. So we've gone from having a low-powered test which was giving a non-significant result to a high-powered test which is giving a significant result, which implies that our failure to reject the null hypothesis originally was indeed probably a type 2 error. We don't know that for sure. We could easily have ramped up the sample size and found that the means moved and became more similar to each other and there was still a non-significant difference, or even that the difference reversed, because of course the underlying principle here is that every individual in the sample is different for random reasons, and that will cause noise. It will mean that each time you do the study you get slightly different results, and we don't know when we're looking at a small sample size whether we're looking at a situation which just happens to have produced this difference between the means by chance. We know there's a 6.9% chance of that happening, or whether it's a real effect but we have an underpowered study and we've made a type 2 error. That's why increasing the sample size is crucial, and it tells us in this case, well, we're very unlikely to have made it's very unlikely that there is no real difference between these means. There's less than a 1 in 100 chance of seeing this difference by chance under the null hypothesis. Okay, so now we would reject the null hypothesis for day 5 and conclude that sperm swim slower even after 5 days after the end of treatment, which then would make us have to perhaps think again about the value of this drug as a contraceptive. Maybe it has a long-term negative impact on fertility, even if that effect is small. And what I've just said there crucially distinguishes between effects which are significant and effects which are large. So just because we've got a nice small p-value, a highly significant difference, doesn't mean that the difference we've observed is big or biologically important. The stats can only tell you about the stats. The stats can tell you what the probability of observing what you've observed is by chance under the null hypothesis, but that tells you nothing about how important biologically any effect that you might have observed is. So that's a really crucial distinction that people often get confused about, and it's one of the reasons why just reporting a p-value is not enough really to tell very much from a scientific study. Yes, it tells us something. It tells us we've spotted a pattern which is unlikely under the null hypothesis, but it doesn't really quantify that pattern, and quantifying it can be really important in terms of understanding the biology. So if we look at the comparison between day 1 and day 5 in the original data sets, what we're saying here is that on further investigation we find that there's a significant difference at both day 1 and day 5, but there's still a really important difference between these two results. Yes, they're both significant, but on day 1 the effect is big. There's an almost 2-fold increase in swimming speed in the control mice compared to the treated mice. Whereas at day 5, the difference is, what's that, about 10% maybe? So you've got a very small effect. We would typically express effect size like this as a percentage. And a small effect like that, 10% reduction in swimming speed, might actually have no real consequences for fertility. It might not significantly reduce the probability of a woman getting pregnant, for example. And so we might say, okay, there is a residual effect of the drug after the man has stopped taking their sort of contraceptive pill, but it's not enough to mean that you can't get pregnant, and therefore it's not something to be too concerned about. So effect size and significance are different things. They are both important pieces of information. If you're reporting a scientific result, you need to be presenting both bits of information. Often the effect size is obvious from the data as plotted in a graph, so that can be enough in terms of the effect size. But you also need to report that p-value, because otherwise you don't know whether what you're looking at could have arisen easily by chance, or if it's so unlikely to have occurred by chance that it probably is a real effect. Okay, that's a really important lesson. Hopefully it's fairly intuitive, but don't forget it, because you'll need to be thinking about that whenever you report a p-value and whenever you do a statistical test, or in fact whenever you do a scientific study. Okay, so we're now going to switch tack slightly and look back at the t-test that we've been doing to consider what assumptions we're making about the underlying data, and then try to deal with situations in which those assumptions are not relevant.